So we're going to do an example here. And we're actually going to do more than what's said, but I'll let you copy the example down here. Okay, so how many recall, I don't know if you, have you ever seen like an ellipse that, if you don't have a cross product term, then the ellipse is going to be like an up and down, well, an ellipse is going to be basically have the origin in its center. Well, these ellipses do have the origin in their center, but you have the major and minor axes for an ellipse. You have the, say an ellipse that looks like this. Hold on, got to get that off. It's not a perfect ellipse, but do you remember from your pre-calculus days that this is, or high school days, this is the minor axis of the ellipse, and this is the major axis of the ellipse here. How many recall that kind of thing? And then you have intercepts. Okay, so of course that ellipse would be one where you don't have a cross product term. When you have a cross product term in the ellipse, you get an ellipse that is going to be something like this, maybe, or something like this. And up to now, for these kind of ellipses here, basically, I mean, I think I remember in high school when I did one like that, I had to plot like 20 points or something, to plot the ellipse, right? Because it's not something that I'm that familiar with, But using quadratic forms, we can plot ellipses like these that are I'm trying to recall the term. One moment. One moment. One moment. There's a word I'm looking for. Oblique ellipses. Yeah, yeah. That's what these are here. These are oblique ellipses, and using quadratic forms, we can graph those quite easily. Let me show you how. So first of all, we recognize that we may orthogonally diagonalize matrix A. And where did I get that A from? Okay, so you know this here, the equation of ellipse can be expressed as a quadratic form, x transpose times A times x. And then, of course, you figure out the matrix A by looking at the coefficients of your variables and the cross product variables. And so you know that 5 and 5 are going to be along the diagonal, and then -4 split in half will equal -2 and -2. And so this is how I get this matrix A here. And we want to orthogonally diagonalize that matrix. So of course we know that we have to find the eigenvalues and the eigenvectors, and that's easily done in MATLAB. Easily done. And the matrix A will equal P times D times P transpose, where P consists of the normalized eigenvectors V1 and V2, and D, incidentally, I guess I didn't write that down, but D is going to consist of, well, let's see, hold that thought for a minute. Let me ask you, I'm going to write something down here. This always happens. Let me clear this. One moment. Okay. Would this be correct? This matrix D here that I've written. So A equals P times D times P transpose, where here's my matrix P, defining it that way, and I'm wondering if the matrix D is correct. Christy thinks it maybe is. Let me ask you this. Do you see a problem with matrix D? I'll give you a hint. The order, the order, the order. Look at the order of your eigenvectors. Well, your normalized eigenvectors. They're still eigenvectors, though. Does the matrix, diagonal matrix D match the order of the eigenvectors or normalized eigenvectors in P? No, it does not. What should come first? The 3. Good. So we'll fix that. We'll fix that. That's better. And so now what we're going to do is, this is the change of variables we're going to use. We're going to let x equals p times y. And I note here that since A equals P times D times P transpose, I showed you this actually earlier, it follows that D, the diagonal matrix, would equal P transpose times A times P. Okay, are there any questions so far? May I move to the next page? All right, Christie's good, my Shaw's good. Okay, Solman's good. Let's go to the next page. So, okay, x transpose times A times x here, which incidentally would equal 5x1 squared minus 4x1 x2 plus 5x2 squared, right? We let x equal p times y. So for the vector x, I substitute p times y. And it turns out that we get y transpose times p transpose times A times p times y, because py transpose is just the product of the transposes in reversed order. But P transpose times AP is the diagonal matrix D. Okay. So we can work out the quadratic form. And we will end up getting that 3 times y1 squared plus 7 times y2 squared. And by the way, that would equal 48, because, 5x1 squared minus 4x1 x2 plus 5x2 squared equals 48. So that means that 3y squared plus 7y2 squared would have to equal 48. And so this quadratic form here, 5x1 squared minus 4x1 x2 plus 5x2 squared equals 48, is equivalent to the quadratic form 3y1 squared plus 7y2 squared equals 48, where the vector y is equal to P transpose times X. If X is equal to P times Y, then Y equals P transpose times X. All right, let me give you a moment to catch up here. Please let me know if you have any questions. Okay. Now, what we want to do is, we know that this ellipse, we know we have an ellipse, and we know what an ellipse looks like, and we know we have an oblique ellipse. So how does doing this change of variable help us? How does this help us? I'm going to show you on the next page. And what I'm going to show you is a graph and some information that's going to correspond to figure 3 in your textbook that comes just before example 5 in section 7.2. May I go to the next page? Are we ready? All right, Christy feels good. Someone's good. Okay, Robin's good. Great. All right. Well, we got to go back in time a little bit. Okay. The vector y is P transpose times X. But remember what this vector is, or this matrix P transpose. It's a rotation matrix, right? That's a rotation matrix. It's a transformation matrix that's going to do a rotation. And the rotation, if remember the rotation matrix, I'm going to double check that, section 1.9. That's back when you learned about rotation matrices. Section 1.9. Yeah, this is example 3, section 1.9. I'm using thetas, but this is the rotation matrix. And this is going to correspond to a rotation transformation. And the theta has to be negative 45 degrees, because that's the only value of theta that is going to work for this matrix P transpose. That's the only value of theta that will work. So what this P transpose matrix does up here, okay, what that matrix does is it rotates the vector x 45 degrees counterclockwise. It rotates this vector, or points, these x1, x2 points, from the x1, x2 coordinate system that you're used to seeing. It's going to rotate those points 45 degrees counterclockwise. Okay, so what I did was I drew a picture here, and I picked on the x1 axis. Well, what I did was I drew an x1 and x2 axis, and based off of that, using this rotation transformation, I get the y1, y2 axes from which I'm going to draw my ellipse. So first, what I do is I say, okay, let's look at 1, 0. If I were to put 1, 0 up here for my vector x point, 1, 0 would get transformed to -1 root 2, to 1 root 2 and -1 root 2. Okay, that's what it would. That's what it would get transformed to. So one of the axes for the new axes, the y vector axes, has to pass through that point, that 1 root 2, -1 root 2, which is the normalized eigenvector, by the way. On the x2 axis, 0, 1, if I put that back in for use that as my x1, x2 coordinate, my x vector, and transform that point is going to get transformed to 1 root 2, 1 root 2 right here. And so the second vector, the vector y, y1, y2, would be 1 root 2, 1 root 2. Well, that means then that the y1 axis has to pass through that eigenvector, 1 root 2, 1 root 2. And so I'm able to draw the y1 axis and the y2 axis based on the eigenvectors. And you can see the clockwise rotation of 45 degrees. This really, I should have -45, right? I have 45 degrees there as because it's a reference angle, but probably, to be exactly right, I mean, we know it's a negative, so let's put a negative in, -45 degrees. There. I mean, how cool is this, right? How cool is this? So now the graph is very easy to do because I mean, our original oblique ellipse could be written as this ellipse, 3y1 squared plus 7, that should be a y2 squared. 3y1 squared plus 7y2 squared equals 48. And I can get make that ellipse in standard form. How do we, like you do here? There's a little bit of work involved, but how many remember standard form of an ellipse? The right-hand side of the ellipse is equal to 1. And then you have the numbers. You have numbers underneath the y1 squared and the y2 squared. How many does that kind of ring a bell? back from their high school days. Okay, Solomon remembers that. Christy remembers that. Well, the ellipse then is going to have y1 intercepts. Okay, it's going to have y, being that there's a 16 under the y1 squared, the y1 intercepts are going to be 4, 0, and negative 4, 0. And being there's a 48/7 under the y2 squared, the y2 intercepts are going to be, well, 0 plus or minus root 48/7, which is, 0 comma root 48 over 7 and 0 comma negative root 48 over 7. And root 48 over 7, by the way, is approximately 2.6. Are there any questions so far? All right. So now, let me just turn my email off. I don't want it to distract us here. Now, okay, so, my ellipse has y1 intercepts 4, 0, negative 4, 0. Well, here's the y1 axis, and I go out 4 units on the y-axis and just put that y-intercept there, and then the other one's over here. And you'll see this matches figure 3 in your textbook. But I give a little bit more detail on how it comes about. And then the y2 intercepts, well, here's the y2 axis. The y-intercepts are going to be 0, negative 2.6 roughly, and 0, positive 2.6 roughly. And now you can draw this oblique ellipse just as you would a ellipse that's not oblique. I mean, with respect to the y1 and y2 axes, our ellipse is not oblique. Our ellipse is oblique with respect to the x1 and x2 axes, but with respect to the y1 and y2 axes, our ellipse is not an oblique ellipse. And that's one of the wonderful things about these quadratic forms. It really, I mean, how many remember maybe in high school, how many graphed maybe a few oblique ellipses or saw them in high school and thought, man, those look tough. Okay, Solomon's seen it. Christy's seen it. Well, now it's not tough anymore because you know linear algebra and you know quadratic forms. And you can do this with other things too, like hyperbolas. Hyperbolas can be written, right, Christy, absolutely. Hyperbolas can be expressed as quadratic forms. You can do the same thing. Yeah, parabolas as well. Yeah, that's right, Solomon. Okay, so how many think this is kind of cool? All right, good, Christy, good, Robin, good, James. Are there any questions? Okay, all right. Well, let me stop the recording here.